Hi everyone, Chen over here, and today I'll be explaining why the space-time dimensions need to be 26 in bosonic string theory in order for quote-unquote the math to be consistent. Okay, so one needs to first understand the concept of ward identities. I'll try to make a video on that another time, but basically when we derive ward identities, there's an assumption that in the path integral, the measure was invariant under the transformations, the symmetry transformations. In the case where this assumption fails, we get anomalies, and in particular for string theory, there's something called a Weyl anomaly that happens, and the Weyl anomaly is actually the reason why we need 26 dimensions. Okay, so we start off from the Polyakov action, and basically this is from the number go to action. We can rewrite it in terms of we can rewrite it into the Polyakov action, which is given as basically a scalar field theory, right? These x mu's, they are originally coordinates in space-time, but now when we write it in the Polyakov action, right, they appear as if they are scalar fields on some two-dimensional theory, and this two-dimensional theory is the two-dimensional world sheet. So in other words, from the number go to action, which is the area of the world sheet of the string, propagating string, when we rewrite it into the Polyakov action, we are kind of reframing, right, the action such that it's now interpreted as a two-dimensional quantum field theory on the world sheet. And it turns out this theory is also a conformal field theory, and that would give rise to a lot of interesting structure. So, okay, so the first thing we notice is that this is a massless theory, right? There's no quadratic term in X, so that means that it's conformal. It is conformal invariance, and that the conformal invariance constitute a part of the one of the gauge symmetries of this Polyakov action. Another gauge symmetry is diffeomorphism invariance, right? Which is basically a reparametrization of the world sheet. In other words, the Polyakov action must remain invariant under reparametrizations. Alright, it must not depend on how we put coordinates on the world sheet. So these two are gauge symmetries of this Polyakov action, and when we quantize it, we want to divide out by the gauge volume, because these are local symmetries, so they are basically redundancies in the description of the Polyakov action. So this is the diffeomorphism invariance in greater detail, and here is the Weyl or conformal invariance in greater detail. So we package both of those gauge transformations up into a single combined gauge transformation as follows, and infinitesimally we see that the gauge transform metric, right, is written as the following, where omega and v are the generators of the transformation. Omega is for the conformal invariance, right, the conformal scaling factor here, and v is the generator of the diffeomorphism, right, as seen here. So this is the gauge transform metric. We'll see this appear later again. So okay, when we want to quantize the Polyakov action, right, we're going to quantize the string theory, we would put it into the path integral as follows. We integrate over all dynamical degrees of freedom, which is the metric and the scalar fields, but we also need to divide out by the gauge volume. If not, we're over quantizing, right? So the standard procedure to handle these gauge volumes is to use the Faddeev-Popov procedure, which basically involves inserting 1 in a clever way, the factor of 1. So this, later we'll see that this Faddeev-Popov determinant, right, which is what it's called, is defined by the inverse of the right side over here. So basically when we insert this quantity into the path integral, right, we see that now we're integrating over all. This d psi is an integral over all gauge transformations, right, as seen over here. So now instead of integrating over these two dynamical variables, we are now also integrating over the gauge transformations, and so when we have the Dirac delta over here also, and basically what that does is initially, right, after when we have this integral, we integrate over all metrics G, but then there's this Dirac delta over here that kills all of them except for the ones where it's equal to the gauge transformed metric. So now the Polyakov action has the gauge transform metric instead of the integral over all metrics. So basically the effect of inserting this Faddeev-Popov procedure is to gauge fix the Polyakov action such that it only it's only calculated with some gauge fixed metric, right? And now instead of integrating over all metrics G, like in equation 21, now we're integrating over all gauge transformations psi. So basically the effect of Faddeev-Popov's procedure is to convert the dg over here into a d psi over here, and gauge fix the metric in the Polyakov action. So the reason why we want to do this is because this d psi over here, this integral over d psi, later will cancel very nicely with the gauge volume, because that's pretty much the definition of the gauge volume is the integral over all gauge transformations. So okay, so all that remains to do, we see that we have done that, which is very nice, but then we've cancelled this term out over here, but then we need to calculate this mysterious Faddeev-Popov determinant. And why is it called determinant? We'll see why soon. So the inverse of it is equals to this integral we need to do, and this term over here, the gauge transform metric, right, when doing it infinitesimally, it's equals to this, which we derived earlier, right? So if this Faddeev-Popov inverse determinant is equals to this path integral, right, this Dirac delta can be Fourier expanded as follows. So the Dirac delta is the integral over IPX, right? We can basically use the Fourier expansion of this Dirac delta to write it as follows. And so now instead of integrating over just the size, we're actually integrating over the generators of the gauge symmetry omega and v as well, and we can see that that there's some terms that appear. So now we have basically we have I, and then this is a term inside the Dirac delta, the Fourier expansion of the Dirac delta, and beta over here is basically acting as p, the momentum variable, the conjugate variable. So that's that. And so now this, we just need to evaluate this integral, but here's the trick: we actually do not need to evaluate this integral, because all we're interested in doing is to calculate the determinant, the Faddeev-Popov determinant, right? And we already have an expression for the inverse determinant. So this, when we look at this integral over here, one can realize that it is a Gaussian integral, right? It's a Gaussian integral because it's a Gaussian integral, and Gaussian integrals calculate inverse determinants. And so how do we calculate determinants? We actually convert the variables over here into Grassmannian variables. So okay, so here's just a proof of why beta is an antisymmetric tensor, right? So so the Faddeev-Popov determinant is written as I believe this should be d omega, right? Sorry for the typo. But the Faddeev-Popov determinant is written as this Gaussian integral over here, and that's the inverse determinant of some operator. In this case, the operator is actually the covariant derivative. So if we want to take the inverse of this, instead of calculating the inverse, right, we want to calculate the determinant. We don't want to calculate the inverse of the determinant. So that corresponds to turning beta and v into Grassmannian variables, anti-commuting variables. This is known as Bayesian integration, and what amounts to is just changing these into anti-commuting variables b and c, and so that gives us a Faddeev-Popov determinant. And if we convert this integral into the Bayesian integral, we get the following thing, which is known as the ghost action. So this is known as BC ghost theory. Yeah. So now the full path integral, right? If we previously we had the following expression for the path integral. Now this path integral, we have found an expression for the Faddeev-Popov determinant. So when we insert that expression into here, then we have an integral over the size, the gauge transformations. But this integral over the gauge transformations, we have integral over x and the size, but this psi disappears because it's just the gauge volume. So we just left over the dx, right? But then the Faddeev-Popov introduces his own dynamical variables, which is the b and c. So now in total we have x, b, and c, right? So yeah, so now this is the path integral that we need to calculate. And it's worth noting that in the Faddeev-Popov procedure, it is common to see anti-commuting variables like disappear, ghost variables, but they are not in some sense they are not physical. They are not physical particles, right? If you quantize it, you will not observe ghost particles in particle collider experiments because they violate the spin statistics theorem. And one can check that we calculate the Feynman diagrams out, they actually cancel, and there's no contribution to there's no scattering amplitudes that involve them. Okay, so now our gauge fixing has we have successfully gauge fixed, right, at the cost of introducing this ghost action. So it'll be useful to work in complex coordinates. So currently we are working over a two-dimensional theory, right? The Polyakov action is an integral over the 2D world sheet. So it'll be useful to convert into complex coordinates. Yeah, and very strictly speaking, if you're integrating over a real manifold, it doesn't make sense to make this coordinate transformation because it involves a complex I. But it turns out I found in my experience that working through most of the calculations with just taking it as a complex variable doesn't really give rise to, we can get most of the correct formulas by just taking it as face value. But if we really want to be rigorous, we need to talk about complex manifolds. But I do not know enough about complex manifolds to shed light on the topic. Okay, so anyway, tensors in complex coordinates, right, are as follows. And if the tensor is symmetric, right, then we get the following simplifications. And if this tensor is symmetric and traceless, then that symmetric and traceless tensors in real space corresponds to the off-diagonal elements being 0. So basically, what's an example of the reason why we're concerned with traceless symmetric tensors is because in conformal field theory, right, the conformal invariance of the theory necessitates that the stress energy tensor is traceless, and since it's also symmetric, right, then basically this is the condition for conformal invariance. This will be a result. The result is that the stress energy tensor in conformal field theory is traceless, which corresponds to this in complex coordinates. That's why we are interested in this case. Okay. So in the metric also, in complex space, the metric also transforms as follows. Namely, it is important to note that in flat space, right, the metric becomes off diagonal, meaning that when you raise and lower the indices, then your z becomes z bar and your z bar becomes z. So the variables kind of interchange when you raise and lower the indices, which is not what we see in the flat Euclidean case. So here's the derivation for the previous slide. Okay, so we can observe that the ghost action, previously we talked about how the Polyakov action is conformally invariant already, but we can see that the ghost action is also conformally invariant, and that allows, conformal invariance allows us to choose isothermal coordinates, which are basically conformally flat metric, to simplify the theory. So if we choose if we plug this equation 66 and 67 into the ghost action, we get the following, right? It simplifies down to equation 74. So all this is just a bunch of index gymnastics to massage it into the right form, but in particular in flat space, right? Because we went into a conformally flat metric, right? The covariant derivatives becomes a normal partial derivative. So the ghost action reduces down to this. So if this is a much neater action, and specifically we see that the Euler-Lagrange equations of motion for this action, it corresponds to B being holomorphic and B bar being anti-holomorphic. Likewise for C, right? So in conformal field theory, the parameter describing the conformal field theory is known as the central charge, and in order to obtain the central charge, we want to calculate the TT operator product expansion. So T is the stress energy tensor, and if you calculate the operator product expansion of these of T with itself, then in conformal field theory that will give me a term that is proportional to the difference in coordinates to the power of -4, and that coefficient is known as the central charge. So we just need to calculate this operator product expansion, and so this is the stress tensor for the BC ghost theory. This is the stress tensor for BC ghost theory. And so when we upgrade it, after we quantize the theory, right, the fields here become operators, right? Quantum field theory turns normal fields into operator values fields. So when we have a product of operators, we need to prescribe it with the normal ordering. So when we multiply two copies of the stress tensor as operators, right, we have a bunch of products of normal normal ordered operators, and these can be handled using weight contraction. So yeah, so in particular, a few of these contractions are zero, but and the only leftover non-zero contractions are the following four operator product expansions. So how do we calculate these operator product expansions? If we consider the ghost theory and put it into the path integral, then if we take a total derivative of this exponential of the action minus the action, then we see that because this is an integral over a total derivative, it should equal to 0. So the fact that this right hand side over here is equals to 0 is due to the fact that this over here is a total derivative. However, if we expand the derivative out, right, we get this ghost action multiplied by this term over here. So basically this over here allows us to say that this is now just the path integral, right? And whenever we stick into the path integral, we know that that will appear as a correlator, right? So this tells us that the correlation function of these two, right, inside the time ordering is equals to the following. In other words, right, the operator product expansion of these two is equal to this. So we see that it's 0 most of the time, except for the point where Z coincides with W, and yeah, so there's that. One can also see that usually, right, in a classical field theory, if we didn't quantize it, right, in a classical field theory, the left hand side over here is 0 because this term is 0. So in other words, what we've shown over here is that the classical equations of motion doesn't hold as an operator equation, because if we consider the correlation with other fields, other insertions into the path integral, they give rise to contact terms. So okay, so we can rewrite the equation 93 as follows, because by using the fact that by using this identity over here. Do note that it might seem weird that the integral, the derivative of with respect to z bar of this function that only involves z, right, is equal to a non-zero value, and the answer is that if this function that only involves z is a holomorphic function, right, in other words, its derivative exists everywhere, then it is true that hitting it with a partial derivative with respect to z bar would give 0. However, this function is not holomorphic because there's a singularity, there's a pole at z equals to 0, which also means that which means that the the derivative with respect to z bar will no longer be 0. So this is something unintuitive that I initially didn't quite understand, but one can go use Stokes' theorem and convert it into complex coordinates to observe this over here. So we get the following by integrating equation 93. We get the following operator product expansion for C and B. Now, if we differentiate this in many different ways, we get all the operator product expansions that we need. So, if we evaluate the TT operator product expansion, then one of the terms looks something like that. I demonstrated it for one of the terms, right? Using Wick's contraction, we can contract for example BZ with this over here, then and the rest is follows, and we get the following expression. Yeah. So the other terms look something like that, and I'll leave you to do the other three yourself as an exercise. It's just tedious, and in the end of summing up all of these, right, we see that we can collect the like terms, and we get that the TT operator product expansion has the following operator product expansion. So you can see that there's this term over here, the difference in coordinates to the power of -4 term, and the coefficient over here is proportional to the central charge. In fact, in general, for all conformal field theories, which is that this central charge parameter describes is a parameter that determines the conformal field theory. Is a key parameter that describes the conformal field theory, and in general, right, the TT operator product expansion will take the following form. So we see that matching with our BC ghost theory, we see that our BC ghost theory basically has a central charge of -26 if we compare these two forms over here. So equation 109 is a general fact of conformal field theories that I did not prove over here, but this is something that's common to all conformal field theories, and our BC ghost conformal field theory is a special case where C is -26. Okay, so the question now is what about other conformal field theories? We just now mentioned that the Polyakov action is a conformal field theory, so what is its central charge? So we start off simple, right? If we have a two-dimensional scalar field, we get a central charge of 1, right? If we have n scalar fields, then our central charge is n. We see that the Polyakov action has d scalar fields, where d is the dimension of space-time. So in other words, initially x mu, right, in the Nambu goto action, x mu was introduced as the coordinates of the space-time string, right? And the indices that x mu the mu runs over, the indices that the mu runs over was the number of space-time dimensions. However, when we talk about the Polyakov action, right, the coordinates of the space-time, the coordinates of the space-time of this string, right, is actually reinterpreted as the scalar field living on the two-dimensional conformal field theory, the two-dimensional world sheet. So in other words, this previously was a space-time coordinate, but now this is a scalar field, right, under the Polyakov action. It's just a matter of interpretation. So if we interpret it that way, then the central charge is just the number of space-time dimensions that the string lives in. So the Polyakov action has a central charge of D. And so previously we saw that we go all the way back over here. If we go all the way back over here where we said that the combined path integral, right, is a Polyakov action plus the ghost action, right? In other words, we're combining the two theories by putting it into the same action. So question is, the Polyakov action has a conformal charge, has a central charge of the D, right, where D is the space-time dimensions. Your ghost action has a central charge of minus 26. Your ghost action has a central charge of minus 26. So question is now, what's the total central charge of this combined theory? And it turns out the central charges just simply add up. So if you go back here, here's the proof of why if you have two theories with no interactions between the fields of the two theories, then the central charge simply adds up. And we can prove so by considering the TT operator product expansion of this combined conformal field theory. So if we do that, we see that these terms over here they vanish because of the following reason here, right? The one field doesn't interact with the other. So the operator's product expansion adds up, and yeah, so the combined central charge is D minus 26. So now we know that total central charge of our conformal field theory is D minus 26. Why is it important to calculate the central charge in the first place? And the answer is because the stress energy tensor, the trace of the stress energy tensor, after being quantized, right, the expectation value is actually proportional to the central charge. There's a way to derive this, which I'll show at the end of the video in the appendix. But one can actually use basic arguments, right? One can just consider the indices over here. So we want to form a 1-1 tensor, right, out of the metric, and the only sensible way to do so is consider the scalar curvature. And this C is kind of just a proportionality constant attached in front of it. So yeah, so namely we see that the right side over here, the scalar curvature is actually not conformally invariant, right? Under conformal transformations, this scalar curvature picks up it is not invariant basically. And on the other hand, right, the left hand side is observable of our theory. It's actually, it must be conformally invariant. So the left hand side it must be conformally invariant because it's a physical observable, right? And if it's not gauge invariant, then that means that gauge degrees of freedom are simply redundancies of the theory. So if the left hand side is observable, it must be gauge independent. On the other hand, the right hand side is a gauge dependent quantity, so we must necessitate that the C is equal to 0, the central charge is equal to 0, and that's only if we want the theory to be physically meaningful, right? There are cases where so this, if we want the theory to be physically meaningful, we call this critical string theory. And there are cases where we actually want to study non-critical strings, right? For example, Liouville theory is something that I'm looking into right now, that involves the Weyl anomaly, but we don't cancel it out by by imposing conditions on the space-time dimensions. So yeah, so basically the reason why we want bosonic string theory, we necessitate that it must be in 26 space-time dimensions, is because we want it to be physically meaningful. And this is the reason why, right? If we want to be physically meaningful, then we must necessitate that C is equals to 0. And so in the end, the combined central charge, right? BC-Ghost theory has a central charge of minus 26. Polyakov action has a central charge of D, which is the space-time dimensions. And if we want to be equal to 0, we must necessitate that D is minus 26. So that is why bosonic string theory requires 26 space-time dimensions. Well, it's worth noting that if we want to be physically meaningful, right, meaning it appears in real life, then actually bosonic string theory is not the candidate, because it doesn't contain fermions. So actually we want to consider superstring theory, which will lead to a central charge of which will lead to a space-time dimension of 10, right? But that's a story for another time. So in other words, this calculation is more pedagogical in nature, because we actually don't really bosonic string theory doesn't describe nature, so it's more like a pedagogical tool for stepping towards superstring theory. So okay, as I promised, I'll show you the calculations for the Weyl anomaly. I'll just step through these slides because it's just a bunch of tedious calculations. Yeah, and I thank you for your time.